Welcome to the first of 3 web seminars about transforming fluid power. This seminar is about transforming hydraulics, and we'll be talking about rethinking the power formulas and the way we apply fluid power. We will also look at eliminating restrictive flow controls. My name is Dan Helgerson. Some new terms will be used in these presentations that should become part of our fluid power vocabulary. Fixed displacement transformer, variable displacement transformer, energy units, units of power, pulse frequency modulation. Be on the watch for them as we go through the presentation. Flow means go. Well, not exactly. It is not that we need to learn new things. We simply have to think more deeply about the things we already know and have sometimes taken for granted. One of the most common misunderstandings about fluid power is the relationship between flow and pressure. It is hard to convince someone that increasing the pressure in a system will not increase the speed when the technician just finished increasing the pressure and things are going faster. If the system in question has restrictive flow controls, or even if it only has plumbing that functions as a restrictive orifice, increasing the system pressure upstream from the restrictions may increase the flow to the actuator. It was the increase in flow resulting from the increase in pressure that made things go faster. Without a pressure differential, there is no flow and so no go. If you were to ask most any hydraulic professional how to make a motor or a cylinder go faster, you would likely receive the answer, add more flow. This is normally my answer too, especially when doing training in basic fluid power. And this is correctly based on our understanding of the relative incompressibility of hydraulic fluid. A fixed displacement actuator, be it a motor or a cylinder, will require a certain volume of fluid to move a given distance. The rate of speed is determined by the rate of flow to the actuator. If someone were to suggest to us that we could slow down a motor by increasing the pressure or speed up a motor by increasing the displacement, we would likely reject that notion immediately. We will have to look a little more deeply at the effect of changing displacement and/or pressure in an actuator. Energy that is transmitted through a pressure-compensated variable displacement pump or stored in an accumulator is always at a pressure that is higher than is required for the load. If it were not, nothing would move. The extra pressure produces unwanted acceleration, and so we find ways to skim off the extra pressure to get the volume of fluid we need at the rate that we require. We are so accustomed to this concept that we take for granted the need to toss away the excess energy supplied from the pump or the accumulator. The energy loss is simply considered the cost of control. Let's take a look at the power formula for angular velocity. We know the equation for power when given torque and RPM. We also know the equation for torque when given displacement and pressure. We can combine these two equations to solve for power using displacement, pressure, and RPM by using our equation mixer. And here we have a new power equation that we're going to be using throughout the rest of the slide presentation. We will also look at the power formula for linear velocity. We know the equation for power when given flow and pressure. We also know the equation for flow when given diameter and linear velocity. We can combine these two equations to solve for power using linear velocity, diameter, and pressure. By using our equation mixer, we come up with a new formula again that we'll be using in the remainder of the slide program. Now the power formulas for both angular and linear velocity show us some things. If we remove the constants, we find that power is proportional to the product of pressure, displacement, and velocity. There is an inextricable relationship between pressure and flow that must be understood when we are talking of power transfer. For any given power requirement at a given RPM, there must be a discrete product of pressure and displacement. For any given power requirement at a given velocity, there must be a discrete product of pressure and diameter. Let's try it out for angular velocity. And what we're going to do, we're going to solve for RPM. So for power, put in 10 kilowatts. For K, we know that it's 60,000. For pressure, put in 20 MPa, and the displacement will be 10 cc's. When we solve for this RPM, we get 3,000 RPM. Now, change the pressure to 21 megapascals. When we solve for this, we solve this equation for RPM, we get 2,857 RPM. An increase in pressure caused a decrease in RPM. At first, this is counterintuitive. An increase in pressure would cause the expectation of an increase in flow, but in these equations, we only changed the pressure. The power and displacement stayed the same. Now, looking at linear velocity, again, what we're going to do is we're going to solve for velocity this time. And we'll use some of the same numbers. We have 10 kilowatts. We're going to have 20 megapascals. And the diameter is going to be 50 millimeters. K is 0.00783. When we solve this for velocity, we get 0.255 meters per second, or about a little over 10 inches per second. Now, change the pressure to 21 megapascals. When we do this, when we solve for the velocity, we get 0.243 meters per second, or a little, almost 10 inches per second. Again, an increase in pressure caused a decrease in velocity. This is counterintuitive. An increase in pressure would cause an expectation of an increase in flow, but in this equation, we only changed the pressure. The power and diameter stayed the same. According to the power formula, if a pressure-compensated pump is used to drive a fixed displacement motor under constant load, you could establish the motor RPM by the pressure setting of the compensator without the use of restrictive flow control. With a fixed displacement motor, if N, P, and D are constant, P must also be constant. A constant power input at a constant pressure with a fixed displacement must yield a constant RPM. And the same is true for the cylinder. A constant power input at a constant pressure with a fixed displacement actuator must yield a constant velocity. We need to think differently. Instead of separating flow and pressure as two different entities, we need to combine them into a single unit of power. Much like in electricity, where the volt-amp is the unit of power, we need to think in terms of pressure flow as our unit of power. 1 megapascal at 1 liter per minute equals 1 unit of power of a megapascal liter per minute, or 1 psi at 1 GPM equals 1 psi GPM unit of power. 1 unit of power can be made up several ways. One could be 0.1 megapascals at 10 liters per minute, or 2 megapascals at 0.5 liters per minute. Or it could be, in the US customary system, 0.1 psi at 10 GPM, or 2 psi at 0.5 GPM, or any combination of pressure and flow that equals 1 unit of power. Stored energy should also be thought of as a volume of energy units. 1 cc at 1 megapascal equals 1 cc megapascal energy unit. A 1 cubic inch at 1 psi would equal 1 inch-pound energy unit. And again, it can be made up in several different ways. Any combination of volume and pressure that equals 1 energy unit. An accumulator holding 50 liters at 10 megapascals has the same potential energy as an accumulator holding 25 liters at 20 megapascals. When we think this way, we are closer to finding a way to use flow, but not at the expense of pressure. We can determine energy requirements in terms of units of pressure and volume. We can determine power requirements in terms of units of pressure and flow. And we can understand the potential energy stored in accumulators and hopefully not be too willing to toss the excess away. My torque isn't working. Here's a pop quiz. Choose the best answer. Torque describes A, effort, B, work, C, power, all of the above. Well, the fact is torque does not require any movement, but work requires movement. It's effort over distance, and so it can't be work. Well, power requires work over time, and so it can't be power, and that means that it can't be all of the above, and so we are left with effort. Torque describes effort. This distinction is important as we move forward in our understanding of energy usage with fluid power. Putting in a good effort is not the same as actually finishing the task and may be a waste of energy. Putting in too much effort is also a waste of energy. In our fluid power systems, we want to provide just the right amount of effort to get the job done without waste. When we do not apply enough force to move a load, or when we intentionally stall a motor or clamp with a cylinder, effort is being applied, but no work is being done. The effort applied and the rate at which it is applied determines the power being used. Using stored energy. Here we have a load of 25,000 pounds that is being held up by a column of fluid. We're going to assign some measurements here. It's a 4-inch bore cylinder. We have lifted the load 12 inches. What would you expect the pressure to be at this gauge? Well, when we divide the load by the area of the cylinder, we find that we have 1,989 psi. What would be the potential energy of the load? Well, we've raised 25,000 pounds 12 inches, so that means that we have 300,000 inch-pounds potential energy. How many cubic inches are in the cylinder? Well, multiplying the area times the stroke, we wind up with 150.8 cubic inches. Now, when we multiply the fluid volume by the pressure without doing any rounding, we get 150.8 cubic inches times 1,989 psi equals 300,000 inch-pounds. Each cubic inch has been charged with 1,989 psi to provide the stored energy of 300,000 inch-pounds. The energy will be used to move a load in and out. Here we have a cylinder with a 3/4 inch rod and a 5,000 pound resistance. We have a 2-inch bore cylinder and we're going to have a stroke of 6 inches. How much pressure would it take to extend this cylinder? Well, we take the load of 5,000 pounds, we divide it by the 3.14 square inches, and we wind up with 1,592 psi. To retract it, we're going to have a little higher pressure because we have the cylinder rod in the way, and we're going to find that we have 1,852 psi required to retract the cylinder. The volume in the blind end of the cylinder will be 18.85 cubic inches, and the volume in the rod end of the cylinder would be 16.2 cubic inches for a total of 35.05 cubic inches. The cylinder is intended to extend and retract in 2 seconds. So when we shift the valve, we want it to go out in 2 seconds. And when we shift the valve back, we retract the cylinder in approximately 2 seconds. And as you can see, we also consumed some of our potential energy. But what is actually going to be happening here? Well, we'll shift the valve. Oh, wow. And then we shift the valve again. There is more force than is required. The force translates into acceleration, extending and retracting in about 0.5 seconds. So what do? Of course, we add flow controls. We call them flow controls, but they are actually power controls. Now when we shift the valve, we get just the speed that we want. We have too much pressure available, but we need the volume to extend the load. The power controls consume the extra energy caused by the pressure. Before we began to move the load, we had in storage 300,000 energy units in the hydraulic fluid. However, we had more pressure than we needed, and what we did is we used the power controls to add an additional 462 psi on the rod end and an additional 118 psi on the blind end to control our speed. So the net result is we were left with 230,273 energy units in storage. Now when we find out what we had minus what we used, we wound up using 69,727 energy units. Now we had a 5,000 pound load that we moved a total of 12 inches, 6 inches out, 6 inches back, and that would require a total of 60,000 energy units. We needed 60,000 energy units. We consumed 69,727 energy units, and that tells us that we used an additional 9,727 energy units beyond what was needed for the load. How many of our energy units were used to move the 5,000 pound load, a total of 12 inches? Well, 35.05 cubic inches of fluid was consumed, each charged with 1,989 psi. 35.05 cubic inches times 1,989 psi equals 69,727 energy units. Only 60,000 energy units were needed to do the work. In order to control the speed, a restrictive load was added to counteract the excess acceleration. The meter out flow controls added an additional load of 1,249 pounds extending and 370 pounds retracting, so that the full 1,989 psi times 35.05 cubic inches, or that many energy units, were consumed. There was enough energy stored in each cubic inch so that only 30.2 cubic inches were needed to do the work. But the fixed displacement cylinder needed the volume. 69,727 energy units were consumed, but 9,727 energy units were tossed away as heat across the power controls. Is there a way the excess pressure could be transformed into flow so that less flow could be drawn from the source and all the pressure could be used? What if we could have actuators that only draw the energy needed to do the work? If motors could torque, we've been talking about referring to volume, flow, and pressure as energy units or units of power instead of separating them in our design thinking. We have raised the question of finding a way to transform the energy units in a way that would be most efficient and not force us to use more than is necessary. Can we make it so that we can maintain velocity by changing the flow from the source instead of the pressure when the loads change? Well, we already have a way to do this with hydraulic motors. we are simply describing a variable displacement hydraulic motor. What we will do differently is control the motor using only RPM as the determining factor. If you recall, we took the power formula for angular velocity and combined it with the torque formulas of our equation mixer to get the new power formula that uses pressure and displacement. For any given power requirement at a given RPM, there must be a discrete product of pressure and displacement. Here we have a variable displacement motor with a maximum displacement of 100 cc's that is to be run at 1550 RPM. The torque load is going to vary from 20 Newton meters to 320 Newton meters. A pressure compensated pump set at 23 megapascals with ample flow capacity supplies the motor. A sensing device, not shown, will monitor the RPM and control the displacement of the motor. The power formula for angular velocity will show us how to maintain the RPM without a restrictive flow control. Using the chart below, we'll see what happens. When the torque is at 320 Newton meters, we're using 52 kilowatts with a displacement of 87 cc's, and our flow rate from the source is 135 liters per minute. When the torque drops to 300 Newton meters, we're down to 49 kilowatts of power, but the displacement has also dropped to 82 cc's, and the flow from the pump has dropped to 127 liters per minute. And as we can see, as we move down the list here, we finally get down to a torque of 20 Newton meters. I'm only using 3 kilowatts of power. My displacement has dropped all the way down to 5 cc's, and I'm only drawing 6 liters per minute from the source. I have been able to, with the use of the displacement control, responding to RPM, change the displacement to match the new power requirement. When the PC pump is replaced with an accumulator, the advantage of using the RPM-controlled motor becomes even more evident. With the PC pump, we had a variable flow and a fixed pressure. Now we have a variable flow and a variable pressure. The accumulator will be fully charged to 30 megapascals. And for simplicity's sake, we will maintain a constant torque of 250 Newton meters and a constant RPM of 1550. The power equation shows us that as the pressure in the accumulator drops, the motor displacement will increase and the flow from the source will also increase. In the current condition, to maintain that RPM with the available pressure, I would need to reset my displacement to 52 cc, and I would be drawing 81 liters per minute from the source. As I begin to drain the accumulator, when I arrive at 25 megapascals, I find that I had to increase my displacement to 63 cc's, and I'm now drawing 97 liters per minute from my source. And this process continues until I get all the way down to where I only have 16 megapascals available. I have increased my displacement up to 98 cc's, and I'm drawing 152 liters per minute from my source. The displacement control, responding only to the RPM, will change the displacement to match the new power requirement. The RPM-controlled motor, supplied by either the PC pump or the accumulator, always draws only the units of power needed. Using a pressure compensated flow control to maintain the RPM throughout the pressure changes in the accumulator would require a constant displacement of 98 cc's, a constant flow of 152 liters per minute at an average pressure of 22 megapascals. The maximum power draw would be 76 kilowatts. the average power draw would be 56 kilowatts. Using the RPM-controlled motor required an average displacement of 76 cc's, an average flow of 118 liters per minute, at the average pressure of 22 megapascals. The constant power draw is 43 kilowatts. The pressure compensated flow control consumed 2,156 power units. The RPM controlled motor used 1,672 units of power. This translates to an energy savings of 23%. An RPM controlled motor supplied by either a PC pump or an accumulator draws only the units of power needed. Electronic methods of sensing and controlling the RPM work well, but may be cumbersome and expensive. It would be better to have an internal system, one that would sense the RPM based on internal signals from the motor. The motor has chambers that produce a discrete number of energy pulses for every revolution. There is a discrete pulse frequency for any RPM. Using this pulse frequency to control the displacement of the motor can eliminate the external electronic control system. If the compensator is hydraulically controlled, a pilot line from the pulse location signals the compensator. If the compensator is controlled by a solenoid, a discrete pulse signal generated from the shaft RPM is used to signal the compensator. In either case, an adjustable spring sets the RPM. This is referred to as pulse frequency modulation, or PFM. Divide and conquer. Understanding the displacement flow divider. For those of us who are unfamiliar with this old technology of this type of flow divider, let me give a brief explanation. The device is made up of two or more separate fixed displacement motor pumps that are mechanically connected. The most common configuration of this type of flow divider is with rotary gear motor pump sets. This is why it is often referred to as a gear flow divider or rotary flow divider. The fact is, any combination of positive displacement motor pumps could be used. In our discussion, we will refer to them as fixed displacement transformers, or FDTs. The most common symbol for the FDT is a group of fluid motors, in this case two, which are touching, as in Figure 1. Because the device both drives and is driven by the fluid, a more accurate symbol is shown in Figure 2. This is the symbol we will use in our discussion. When flow enters the unit at one side, it is divided proportionally based on the displacements of the sections. What makes this different from a spool-type flow divider is the fact that the power is not restricted, but merely divided proportionally. The sum of the power exiting will equal that of the power entering. For example, with a two-section device of equal displacement, if 20 liters per minute at 10 megapascals exit from one port and 20 liters per minute at 0 megapascals exits from the other port, a total of 40 liters per minute will have to enter at port 1 at a pressure of, you got it, the input pressure would be 5 megapascals. Power in equals power out. 40 liters per minute at 5 megapascals equals 20 liters per minute times 10 megapascals plus 20 liters per minute at 0 megapascals. The FDT has been around for a long time. It is not compact and cannot easily be contained in a manifold. It is not adjustable. A typical 50-50 unit will divide the flow in half, plus or minus 5%, depending on the pressure difference between the outputs. When compact restrictive flow dividers were developed, the displacement divider was relegated to applications where size and accuracy were not a priority. very little attention was paid to the energy advantages that could be gained by its use. Let's take a look at several applications of the FDT, some of which are often overlooked. We will limit our discussions to devices with only 2 sections. The examples are not intended to be fully operational circuits, but are ways that the transformer could be configured. First of all, of course, is the flow divider. We have an input flow that is divided equally on each side, or divided proportionally on each side. It can also be used as a pressure intensifier. In this case, as you can see, we have one side that is returning to the reservoir, the other side is going to do work, and you wind up with a reduced flow but higher pressure on the working side. It can be used as a flow augmenter. If we reversed it, we find that the upper device can be used as a motor to drive the lower device as a pump. The 2 flows are combined, and we wind up with twice the flow at half the pressure. It can be used as a kidney loop, and this is an often overlooked method of doing this, but the fact is we could take return line or parasitic losses from our system. We could then use a gear flow divider, if you will, or a transformer to then take some of that flow, drive it, use it as a motor to drive the pump to feed our kidney loop. 2-speed, 2-force cylinder clamp. Here we have a situation where in normal operation, the cylinder would extend at a relatively high speed, and then once it came to the end of its stroke and the pressure became high enough, the valve would shift, and we would wind up with pressure intensification. And we could do the same thing with a motor, 2-speed, 2-force motor. We can also regenerate a motor circuit. Wait a second. How can you regenerate a hydraulic motor? Well, let's take a look. With the directional valve in the pictured condition, all flow from the transformer passes to the reservoir. The motor speed is determined by the source flow. When the directional valve is shifted, half the flow goes to the reservoir while the other half joins the source flow. The motor goes twice as fast, but at half the torque, without changing the source flow or the motor displacement. Now, an FDT is not really a flow control. It is a flow divider combiner. It splits or combines flow and pressure in proportion to the ratios of the displacement sections. This is why some people refer to them as power proportioners. They do not limit flow or pressure, but merely proportion whatever units of power are flowing through it. What is needed is a way to use the transforming powers of the FDT to mold the transfer of energy in a way that will provide true energy control, not just flow control. We will combine what we have learned about the transformer with the perspective of using units of power. What we are about to see is a new displacement device that will enable us to let each actuator draw only the energy units needed for the work being done. When we think of power as a rate of energy unit input, we can see how controlling that energy can provide speed control without the use of restricted flow controls. Introducing the Variable Displacement Transformer, or the VDT. The VDT is simply a single 2-chamber positive displacement device with the displacement of each chamber dependent on the displacement of the other. It is placed in the fluid stream in such a way as to divide or combine energy units, much like the pressure flow transformers on the previous slides, only with infinite variability. It can proportion the energy into 100% to 0%, or 0% to 100% ratio, or anything in between. The suggested symbol on the right shows a single rotary device with 2 chambers. Each one is dependent on the other, and each one can be driven by or drive the fluid energy passing through it. It is infinitely variable. We will use the power equation and take the example of the motor regeneration circuit using the fixed displacement transformer but replace the FDT with the VDT and require a constant RPM. The motor exhaust is directed to the VDT inlet, where it is divided between the chambers of the transformer. An adjustable orifice sets the pressure drop that controls the compensator of the VDT. The pump compensator is set at 21 MPa. The fixed motor displacement is 100 cc's. The required speed is 1000 RPM. The default condition of the VDT is for 100% of the motor exhaust flow to be directed to the reservoir from port T2. Port T1 joins the flow line from the source. The K-strain flow will be 5 liters per minute. So what will be the flow required to achieve 1000 RPM from the motor? It will be 105 liters per minute. That means I will need 105 liters per minute coming into my fixed displacement motor all the time. Initially, that means I'm going to be drawing 105 liters per minute from my source. It means I'm going to have 100 liters per minute in my exhaust flow from my motor, and I will have 100 liters per minute going to the tank through T2. I will have 0 liters per minute from T1 joining the source flow. What will be the pressure on line T1? Well, as you can see, T1 is connected to my source, and so the pressure would have to be the same. And so the pressure on T1 will have to be 21 MPa. So in my beginning condition, I have a torque of 318 Newton meters, and with an effective pressure of 20 MPa, I will be drawing 33 kilowatts of power. Now what I have is at the outlet of the motor, I have a resistive pressure, and so what I'm showing in my formula is my effective pressure. It's just the inlet pressure minus the outlet pressure gives me my effective pressure. And what you will see as we go through this now is you'll see a constant reduction in my effective pressure because I have a constant increase in my resistive pressure, and we're going to see that my horsepower, my kilowatts are going to be dropping, and my flow from my source will be dropping as well. So as we go through this, we see that as my torque decreases, we just go down and down and down until I finally get to my minimum situation. And here I am with minimum torque, actually 0 torque, and I have no more flow moving anywhere, nothing is happening. The VDT is controlled by the delta P across the adjustable orifice. This fixed displacement motor will have a discrete exhaust flow of 100 liters per minute at 1000 RPM. As the torque load decreases, the motor will try to accelerate, increasing the flow and consequent delta P across the orifice. The VDT responds by changing the ratio and increasing the flow through T1. You can see this happening here. Until we come down to very low torque, we find that the pressure at the motor exhaust is determined by the ratio of the displacement times the output pressure at T1. Power in equals power out. When 10% of the motor exhaust is directed to the tank at very low pressure, the pressure at the inlet to the VDT will be 90% of the output pressure at T1. This pressure becomes the resistive pressure that reduces the torque and is the force that drives the regenerative flow. Notice that as the torque changes, the flow from the pump also changes, and that all the units of power that come from the pump are used up as they return to the reservoir. If 1 unit of power equals 1 megapascal liter per minute, then with a torque of 318 Newton meters, 2,000 units of power are used. With the torque at 60 Newton meters, 377 units of power are used. The VDT functions much like a pressure-compensated meter-out flow control. It produces a resistance that consumes the extra energy in the motor. But instead of extracting the energy as heat, the VDT returns the energy to the flow source. All the pressure is used all the time. It is the source flow that becomes the energy variable, not the pressure. The VDT causes the motor to draw only the units of power needed from the source. Will the VDT work on a linear device? Well, the power formula for linear motion should tell us. For any given power requirement at a given velocity, there must be a discrete product of pressure and displacement. The fixed displacement motor has been replaced with a cylinder. The cylinder has a 112 millimeter bore, a 1 meter stroke, and a 50 millimeter rod. The effective diameter of the cylinder is 100.22 millimeters. It will travel at 0.21 meters per second. With an effective pressure of 20 megapascal, there is a maximum force of 158 kilonewtons. As the load varies, the inlet pressure remains the same, but the force matches the load with the extra energy being returned to the source. When the resistive pressure reaches the source pressure, the forces are balanced and the cylinder floats. A fixed displacement actuator, whether a motor or a cylinder, will have a discrete exhaust flow for any given velocity. This exhaust flow, passing through the transformer system, is used to control the velocity. There is no need for the restrictive flow control. Replacing the VDT with a restrictive pressure-compensated flow control causes the system to draw maximum energy throughout the cylinder stroke. If the cylinder were to begin at no load and then continue through its stroke to maximum load, there would be an average pressure of 10.5 megapascals, and it would require 1,050 units of power. The restrictive pressure compensated flow control system consumed 2,100 units of power. We needed 1,050. We used 2,100. That means we wasted 1,050 units of power. The restrictive flow control consumed 1,050 units of power as heat. The VDT provided a 50% energy savings. So now what do we do? There are several versions of the VDT currently at some stage of development. There is an axial piston version developed by Peter Achten at NSBV in the Netherlands. There is a rotary vane concept that is being pursued, which will be described and discussed in the next web seminar. And Dennis Rankin is working on a unique variable gear displacement transformer as well as a double piston device. None of these are currently at your local distributor. If the VDT and the PFM control motor do not yet exist, then why are we talking about them? Well, we have learned in this seminar that we need to think differently. We need to think in terms of energy units and units of power, and this enables us to better define system efficiency by comparing actual work accomplished with the energy entering the prime mover. We will view the restrictive flow control and the pressure reducing valve for what they really are: power parasites. As we become more aware of the inefficiencies, we will be looking for solutions. And when the VDT and the PFM controlled motor become available, we will be ready to embrace them. So, what do we do? Well, remember, we said we need to think differently. Review this material. Check the math. Analyze the circuits. And when you are confident that it will work, find an application where you can try it out for yourself. You don't have to have a VDT to try out the concepts. You can use existing FDTs to make application and help gain confidence. Here we show a 4-section VDT used as a 4-speed transmission. The outlet of each section passes through a 3-2 valve that directs the flow either to the reservoir or to the power source. The throttle valve, V1, could be a foot pedal or a proportional solenoid valve, determines the angular velocity of the motor. The VDT determines the torque available from the motor. The FDT determines the torque available from the motor. Valves V2, V3, V4, and V5 are set at progressively higher pressures. At startup, the motor is at full torque and can accelerate quickly to the throttle setting. If the motor tries to exceed the throttle setting, the increase in pressure behind the throttle shifts V2, 3, 4, or 5 to reduce the torque. Go back and look at the applications for the FDT that were shown in earlier slides. Replace one section with a variable displacement motor. Couple two variable displacement motors together to create your own VDT. Think differently. You may request a free copy of the series of articles about transforming fluid power that appeared in the Fluid Power Journal by going to danhelgerson.com/webinar. Or to send questions or comments, please go to danhelgerson.com and select the Contact tab at the top of the home page. Thank you very much for your attention.